In this training video, we're going over a live teaching demonstration at our shop in reference to checking the refrigerant charge of an air conditioning system. So we have a running air conditioning system. We're going over all of the pitfalls and the little details that really matter when measuring the refrigerant charge level to see if you're undercharged, correctly charged, or overcharged. And so if you want to get a more slowed down, methodical approach to this, make sure to check out our refrigerant charging and service procedures for air conditioning book. So that's available over at Amazon and at acservicetech.com. And so now we're going to go ahead and get started. We're using pressure to convert it to temperature. And so you have this line right here. So this is the large line. That's low pressure. Large, low pressure, suction, blue. So a lot of times we are maybe starting off in the trade using something like this, a manifold gauge set. And then maybe we move over into something smaller like a quick connect test gauge. Maybe we use something like this, like a digital gauge, digital probe. We could move over to something like this, a wireless probe. And so the object is, I'm going to show you how to connect into this with a regular gauge set. A lot of people are familiar with that, but we are moving away from that in order to monitor pressure because we're trying to avoid contaminating the refrigerant oil. So the large line is what? Is that the high pressure side or the low pressure side? Low pressure side. And the small liquid line, what is that? Is that the high pressure side or the low pressure side? High pressure side. And so the high pressure side, do you know if that is that vapor or liquid on the high pressure side? Does anybody know? Vapor. On the liquid side? On the small liquid, oh sorry, on the small, I gave it away. So on the small liquid line, small line, that's liquid. So small liquid, red, high side, okay? So that's going to be the high pressure, liquid. Think about boiling in a pot. You want to think about that. That's what's happening in this line. It's all boiled with no liquid left. It should all be boiled. In this, it's all packed together real tight. And so you can provide a liquid, a column of liquid in a smaller tube. That's a way to think about it. Also, you can think about the low pressure is going to be also what temperature? Low pressure is what temperature? What? Low temperature. So low temperature, low pressure. So we're going to put the blue gauge over here and the red gauge on the small liquid line. All right, so when we measure on the large vapor line, we're measuring the low pressure vapor coming from the indoor coil, and the small line is going to be the high pressure liquid from the condenser. And really, even though we're measuring pressure over here, we're actually measuring pressure in the middle of this coil. Even though we're measuring pressure here on the small liquid line, we're measuring pressure in the middle of this coil. And so we're going to go ahead and do it. So I'm going to go ahead and have my safety glasses on. And so on this manifold gauge set right here, I'm going to first start with the handles shut. We want to make sure that our pressures are zeroed on the gauges. If not, we can adjust them right here. If you have digital gauges, same thing. When you turn them on, you want to make sure that they're at 0 psi. Does anybody know what these are called? Mechanical? Pretty good, yeah. Manifold. This is the manifold right here. So this will be a manifold gauge set. And these are compound gauges because the needle can actually go into the green or over into the blue on this particular gauge. Compound can go both ways. It's a mechanical manifold gauge set. So I'm going to have these shut. I'm going to go ahead and connect the blue gauge in. Over here we have a cap. So we have a port cap. We're actually required to have locking caps. So anywhere where it's accessible, we don't want somebody that's not a refrigeration technician accessing these ports. So with this shut, we can go ahead and attach right into our our large vapor line, sorry. We don't want to have any air getting into the refrigerant, and the longer I let this sit here, all this refrigerant is mixing with the air. And so what I'm going to do is I'm going to shut this valve. These are low loss fittings on the end of the hoses, manual low loss fittings. You could have automatic low loss, but these are manual, so right now this is open, and what I'm going to do is I'm going to close it. I'm going to open up the blue handle, and remember this valve is shut. Do you see this valve? This is a valve core removal tool. I just put it right here. And now I'm going to go ahead and open up my red handle. So what I just did is I purged the air out of both hoses. How long does it take to do that? What is it? About a second, 2 seconds, something like that. It's a little hard. It's a little hard to know exactly how long. You're not going to see like liquid flash. You don't want to release refrigerant into the atmosphere, but you also don't want to get air into the system accidentally because you're going to mess up the refrigerant charge. All right, so now that we purge the air, we're going to make sure that we have our handles shut, which is what they are. They're shut. I'm going to connect in. What happens like when we connect in and you have like a bunch of refrigerant coming out? Does that happen to anybody? Yes? What do you think like is wrong in that scenario? Something's wrong with your hose end? Yeah, you could do it quicker. Do you wear any gloves? You wear thick gloves? You wear like thin gloves? Nothing? Nothing? So the object is we don't want to get that absorbed into our bloodstream. It can lead to like brain defects and things. So we don't want to be dumb. We want to be smart. So you see this little rubber grommet on the end of the hose? If this is worn and it's too far in, you're going to have a lot of refrigerant kind of spewing out as you go to connect. You're going to want to replace those O-rings. So those O-rings look like this, or look actually called gaskets, not O-rings. Yellow Jacket makes a nice little replacement pack that you can do. In the inside right here, this little brass piece, that is a valve core depressor. So this is pressing in on this little valve core. What do you guys call this? Schrader valve? Schrader valve or valve core. This right here can be used to replace a valve core on an existing system without releasing the refrigerant and without having to recover all the refrigerant out of it. You can actually pull the valve core out of the port in order to replace it, but that's a valve core removal tool. On the end of the hose, you could have a bunch of different low loss fittings. Here's a automatic low loss fitting. I don't really love these. I really like these right here that you have on the end of the hose. They're actually built onto them. I don't really like these either because you have like an extra connection point. If you were going to shut this off, it doesn't give you a whole lot of control. Like that amount of refrigerant can potentially burn you if it comes out onto your hands. You don't want that to happen. You want more control, so I like to have these manual low loss fittings on the end of the hose. I don't like it to be an additional thing like this. But worst case scenario, you could add these on the end of a regular hose like this. What's missing on the end of this hose right here? Valve core depressor. You see that there is a missing brass piece in the end right here? So if we were to connect the one that does not have the valve core depressor in it, what's going to happen? It's going to leak. Going to leak what? Not going to leak anything. Why? It's not pushing up against the Schrader. Yeah, it's not going to actually push against the Schrader valve in order to allow the refrigerant to the manifold gauge. All right, now we did a little exercise earlier trying to determine what the pressure is in the tanks. Can anybody tell me what pressure is most likely going to be on these gauges right here? Anybody want to come over and take a look?
175.
We're actually at, yeah, so 175 is a large line, another 5 increments, about like maybe 182, something like that. Yep, 182. So it's actually 182, what's that converted to temperature?
182 is 64.
64?
For a 410A system.
For an R-410A system, yes. And so what refrigerant's in this system? How do you know?
You can read the door.
What, the door of what? Over here?
No, the condenser. You can read the door.
Condenser, awesome. Yes, so this is called the condenser. You can read the door right here. And so right here it says R-410A. So you're going to know what refrigerant's in it by reading the tag. What else could you look at to see what kind of refrigerant's in here without measuring the pressure first? What else could you look at? TXV, a lot of times, yep. The TXV, that is a metering device. Well, here, I'll put that right there. TXV metering device, that's one of these. Sometimes they have the refrigerant right in the top of the head. This is a metering device, R-410A right there, right? R-410A on the top. Of course, you'd have to open the evaporator coil in order to see that. See that? Is there anything else that you could look at? What?
The compressor.
The compressor? Yeah, a lot of times you're going to have a tag, the rating plate on the tag of the compressor down in there will state what refrigerant is in this system. So there's several things that you could do. All right, so right now we have saturated refrigerant throughout the entire system. And if we were going to go ahead and turn this on, right now the saturated refrigerant through the whole system, where is the saturation going to be at when we turn this on?
Coil? Evac coil?
The evac coil. Is that the only place that that's going to occur at?
Outdoor coil too.
Yes. So both of these lines. What's going to be in the large line? Vapor. And what's going to be in the small line? Liquid. Great. Awesome. Awesome, awesome. All right, so we all plugged in. You want to go ahead and start her up? Now, before we do that, what we're going to do is we're going to go ahead and, yesterday we did, does anybody check the refrigerant charge on systems, you know, a lot? Anybody else? What's something that you need to do before just even hooking the gauges up? Like, why would you hook the gauges up?
Check it. For your pressure.
For what? Why? Why would you do that?
I need to know what's in there.
It's not working.
It's not working? Okay, what would you do before hooking the gauges up onto these ports?
Check the airflow.
Check the airflow? Why would you do that?
Why? ABC, airflow before charge.
Okay. Yeah, so without airflow, airflow is just as important as the refrigerant charge, and so without any air, there's not going to be any heat transfer. So last night we went over how to measure airflow in a system. Now, what's another thing that we could end up, well, we have to check actually before we measure the refrigerant charge. Is there anything else that you think that we should check?
Compressor amp.
So we're going to have to start the system up first before we get an amp draw. But what else could we check on the system? What changes from system to system, like the way it's installed? Is the compressor sometimes different? Is the metering device sometimes different? Is the coil sometimes different? What is the main difference that will separate two charging methods? Anybody know? The refrigerant, knowing the refrigerant, and what else? The metering device. Okay, so this one has a fixed orifice. This is a piston. So we're going to be using the total superheat method because this right here cannot control the superheat that's occurring in this coil. So we're going to be primarily checking this low side gauge, and we're going to take this pressure and we're going to convert it to temperature. We also are going to need a temperature on that vapor line. And so as well, we're going to just monitor the temperature that's in the room. So we're going to turn this little bead temperature sensor on. Why don't you guys come over here so you guys can see? If you want to come over on this side or over here, wherever you want to go, just so you can see what's happening here. All right, we're going to turn this on. Hard. So, what we see here, when the system turns on, this pressure right here is going to rise. This pressure right here is going to lower. Pressure's on the outer ring on these compound gauges. This is a compound manifold gauge set. It's a 3-port. When this handle is shut, we're able to measure the pressure on the red line. When this handle is shut, we're able to measure the pressure on the blue line. So we have a low pressure. Where is this measuring the pressure at? Where? The low side, which is that the low side or is that the low side? Pressure side. Right in here, right? Yeah, in the evaporator coil at the air handler. So this is considered an air handler. Some people call it a fan coil because there's a fan. There's a fan in here and a coil in here. During the first 3 minutes of runtime, I like to monitor the pressure, well, I'm actually monitoring the temperature in that coil. So if we already know we have a clean filter, we measured the airflow like we did last night, we know what type of metering device is in here, we know we're measuring with the total superheat method because there's a fixed orifice in here, then we know we have to check with the total superheat. And what Ty was mentioning with that earlier is if we know the pressure in the middle of this coil, we can convert it to saturated temperature. So right now, I'm just going to ask you, we have a pressure on the low side of 123 psi. What R-410A saturated temperature do we have on your PT chart? Yeah, sure. We have now we have 125 psi on the blue gauge. Convert that to the R-410A saturated temperature in the middle of the coil. What's the temperature in the middle of the coil? 43? Yeah, I'd say about that, 43 degrees. All right, now we have the temperature on the large vapor line, and that is on T1. We have a temperature of 45, 46 degrees. So, we're not able to measure the superheat right here, but because we're all the way out here, we're calling it the total superheat. So we have the line temperature minus the saturated temperature in the middle of the coil. So if we got 45 minus 43, we have how many degrees of superheat? What is it? 2. So we got 45 minus 43, so we got 2 degrees of superheat. That is not a lot. Okay? What did Ty mention earlier about determining how much refrigerant's in this coil? We can determine it by measuring what? Superheat. If the superheat, the temperature increase of the vapor refrigerant, so what happened is the low pressure liquid, because it went through the metering device, there's a little bit of flash gas. What's happened is now it's gone through the entire coil. It's done its phase change. It's absorbing heat from the air crossing the coil. Remember, it's at a lower temperature than the air crossing the coil. And what's happening now is that it's complete phase change, and now it's a completely vapor state. It is increased in temperature now by 2 degrees in the vapor state. So we know that only a tiny, tiny bit of this is vapor. And this is maximized for saturated refrigerant. Is that good or bad? Well, aren't we, if it's a lot of saturated refrigerant, doesn't that mean that we've got a really good heat exchange going though, right? Huh?
I'm sure it's great for that. It's not so great for us.
Yeah, well, who cares about that? You know? Oh, we should, right? Okay, this fixed orifice cannot control the superheat. We are controlling the superheat by adding or recovering refrigerant out of here. But first, you got to remember from last night, we mentioned the airflow plays a big factor in this. If you change the airflow, you're going to change the superheat. You're also going to change the temperature. What I was mentioning earlier is during the first 3 minutes of startup, I wanted to make sure that my saturated temperature does not fall below 32 degrees. What happens at 32 degrees? What is it? The refrigerant freezes in the evaporator? No. What happens? On the outside of the evaporator coil, it freezes, right? So it's not the refrigerant freezing, it's the humidity in the air gets attracted to the low temperature coil and freezes onto the coil when the refrigerant temperature is below 32 degrees. Is that going to happen right now? We are at 125 psi correlated to what saturated temperature? 43? 42, 43? So is the humidity in the air going to frost onto that coil and turn this coil into a solid block of ice? No. But we do have a danger to the compressor right now. If we only have that small amount of vapor at the top, say we lost it by the time it got from there through this line and over to here, If we lost the superheat and we had 0 degrees of superheat, what does that mean that the state of the refrigerant is? Saturated. What does saturated mean? Is that vapor or liquid? Or it's both? These compressors, they're vapor only. Gaseous state. They pump gas, not like liquid gas. We're talking about vapor only. If you put saturated refrigerant into a vapor compressor, it's going to kill it because it doesn't have enough room to expand. This thing is trying to compress. Can't compress the liquid, you can compress the vapor. You can squish the vapor molecules together. So you're going to have a danger to the system if we lose the superheat. So what I would typically say is you're never going to have, or you're never going to want to set the superheat on any running air conditioning system lower than, say, 6 degrees. Other people might say, oh, you're good to set it up to 5 degrees, 6 degrees. You want to have more vapor in here on a fixed orifice because the amount of superheat will change based on the heat load crossing that coil. So we're talking about temperature in the house. We're talking about humidity in the house. If that changes, your superheat's going to change. So just because you measure 2 degrees of superheat right now, when you leave, say tonight it's getting cooler as the night goes on, you could potentially have this system running with 0 degrees of superheat. Saturated refrigerant goes into the compressor. It kills it because we accidentally overcharged the system. Not good. Not cool. It's not good at all. And so right now, we don't know what the target superheat is. Does anybody know how to find what it should be running at? What target superheat should it actually be at? We're at 2 degrees of superheat. There's a little bit of vapor in here, and the vapor is making it back over here. But how do we know if 2 is right, if 30 degrees is right? 30 degrees technically could be correct. Depends on the day. Does anybody know? What panel? Right here? May have a target superheat chart. Okay. How often is that?
For modern TXV systems, yeah, 210 times.
Yeah. Most systems nowadays are coming with a thermostatic expansion valve because this right here can control the superheat. This thing is always trying to maintain a superheat of maybe, say, 8 to 12 degrees. So it's always trying to keep about this much vapor, say, in the evaporator coil at any given moment, regardless of the heat load to a point. If you have low indoor airflow, this thing can't close down enough to keep the superheat steady. So this has a little pin inside. It can open up or close down the amount of refrigerant going through it. It works on 3 pressures. This is the opening pressure, 1 opening pressure right here. Then you have closing pressures. It's external equalizer and a spring pushing. So it uses 3 pressures, and we'll get into that later, in order to hold the superheat. So this, if you accidentally overcharged it a little bit, it's going to lead to a lack of efficiency, but it's not going to potentially kill the compressor. If you overcharge it a lot, oh yeah, it can't meter the refrigerant down enough, potentially. And if that's holding the superheat steady, and you have a known amount of saturated refrigerant and you keep adding refrigerant in, where is it going? Stacking in the outdoor unit. So you have more and more liquid refrigerant filling the outdoor unit. What do we know about saturation? Like how much room is left for saturation? Less. The more you fill up that coil with liquid refrigerant, the less room there is for saturation, the less heat rejection, the higher the pressures. You're making the compressor work a lot harder. If you overcharge it, it's going to cost you more in electricity. Anyway, get back to this now. In order to determine the target superheat of what this should be, it's going to change from day to day. Right here, these are quick reference cards. We developed these over time, but basically right here, check this out. You see the red or not the blue. You see the blue would mean it's not going to have a target superheat. If it was the outdoor dB temperature, that's like a standard dry bulb temperature. Regular thermometer. Was anybody know what the temperature was outside today? 82 degrees? Okay. 82 degrees. Let's just go with 80 degrees for a sec. We would measure this. See where our temp probe is right here? It's the air entering into the outdoor coil. That's what we need to measure. We're not going to measure it up here because why? It's going to be hotter up there. This is the heat rejection area. This is the heat absorption area. Here is the heat rejection area. So we're measuring it down low where the airflow is coming in. Not in the sun. You're going to have it in the shade. You're going to pull that in. So right now, it says we're measuring about 68, 69 degrees. What I want to show you though is, say it's 80 degrees outside, and we measure what's called an indoor wet bulb temperature. It's a measurement of temperature and humidity. What we do is we use a psychrometer. This is what the old guys had back in the day. There is a mercury thermometer here with a wet sock. And what that's going to do is it's going to be a lesser temperature, basically, than what the dry bulb temperature would be on that same stat. What we would want to do is wet this sock and have that on the bead of the thermometer. Likewise, so we have to have air crossing it, by the way. It's the evaporation temperature. So we would be swinging that like this near the return. Checking the charge, ma'am. You know what I mean? Like, that's not good. That's old. We could take a regular mercury thermometer. We could wet the sock on the end. We could put that into the return because air is now moving, and we can get our wet bulb temperature there. That's a psychrometer. And we can get a digital psychrometer. Just turn it on. Turn it on to wet bulb. And right here, this one measures, say, 59.2. You want to measure the air, the wet bulb temperature of the air, coming in and crossing the indoor coil. It's got a big tip on it, though, right? Can't stick it in the ductwork. So here's this smaller one. Here's another one right here. It looks similar to that hot wire anemometer we had last night. So you can stick it right in there. Turn this one on. We can stick this one in and measure it at the return. You don't want to be like super crazy close to the evaporator coil because it will be more moist in that area. So you know we need a wet bulb temperature. Is that what it says? WB temperature on that chart? And we need a outdoor dry bulb temperature right here if this was outside. So right now, we're measuring a wet bulb temperature 57 degrees. So go over on the wet bulb temperature of the top between 56 and 58. Let's just pick 58 for now. And we got a dry bulb temperature of 69. Let's just call that 70. So 58 in the top, 70 on the side, line it up, and what do we got as our target superheat? 13. Everybody see how that simple that is? All you need is a wet bulb temperature inside the house at the return grill. The problem is if you have leaky ducts. If you have leaking ducts, you could be pulling air from the attic and not from the building. So really, if you could get it closer to where the air is getting ready to cross the coil, that's where you really want to take the measurement at. Worst case, you could take it at the grill, but once again, air leakage, most ducts, like in the United States, are leaking a considerable amount of air, a lot of air. That's a problem. All right, so if we have a target of 13 and we are at 2, let's see where we're at right now. We're still at 125 psi. (125 psi) correlates to what? R-410A saturated temperature in the middle of the coil? What is it? I can't hear you. 42 degrees. So we got 45 minus 42, and we have about 3 degrees of actual total superheat. We've got a target of 13. Does that mean we're overcharged or undercharged?
Well, assuming everything else is right.
What else could be a problem?
Low superheat and along with a couple of other symptoms can be enabled by the riverside meters.
Okay. Okay. So yeah, you're not going to know. Are you able to tell what size metering device is in this system?
No, without taking everything apart. It's typically a good idea to start off with a small change in the refrigerant and see if the system reacts that way it's expected.
Okay. I like your answers. I like your answers. Assuming that was correct, we have a fixed orifice. Assuming that's correct in size to this system, back in the day, these outdoor units would say the piston size. They don't come with that now because all these indoor coils are equipped with a thermostatic expansion valve because they're more efficient at heat transfer. They also are better in a dry climate to save the compressor. So if you have a high target compared to a low actual, that means that you're overcharged. We need to recover some refrigerant out so that the refrigerant level in here can lessen so that the amount of superheat can increase. Does that make sense? If your actual superheat increases, that's the temperature increase of the vapor refrigerant. So say we have 43 psi right here, or I'm sorry, 43 degrees right here, right? If we measured on this line 60 degrees, what is our total superheat? 60 minus 43 is what? 17. If we have 17 degrees of actual superheat and our target's 13, now we're a little low on refrigerant because we have more vapor refrigerant in here than saturated refrigerant. So we're going to need to recover some of the refrigerant. We can do that to adjust the refrigerant charge using a recovery bottle. But before I do that, I just want to show you what happens if I adjust the airflow. Because a lot of people try to skip the airflow area. Okay? So what do you think is going to happen if I lessen the airflow across that coil? What?
Don't do that.
Why?
So you're not compressor.
Why? What's wrong with the compressor? Isn't it going to be happy? It's going to have to work less, right? There's less heat, Carlson? What's the problem?
Well, if you have less air going across, your coil can absorb less heat.
Right.
Absorbing less heat is not heating up. Superheat can drop. And the liquid going back to that compressor. That's not sound very good.
Right. So if you don't have enough heat to boil that refrigerant and for the refrigerant to absorb, you're going to have a big problem. You're going to have saturated refrigerant entering into that vapor compressor. Now this unit, like most air conditioners, will not have one of these tanks right here. This is an accumulator tank. This is a protection device for the compressor. It's also a storage vessel. Most heat pumps are going to have an accumulator tank. And that will only allow vapor refrigerant to enter the compressor. It's right in front of the compressor. But these don't have them because they don't typically need them, at least in our climate. Maybe in the, see right here, this one says installation prohibited in the Southwest. That might be an issue there. It's not here. So we don't typically have an accumulator to safeguard the compressor. There's no way of this system to control the superheat when the heat load reduces, like what you're saying. And so that brings up a whole nother good point. Should we be checking the refrigerant charge like when it's like 50 degrees outside and you're like running your heater in the house? No? Why? Like if we're doing preventative maintenance, we need to check the refrigerant charge. Like we just need to do it. What's the big deal?
There's no load.
There's no load. So as soon as we turn this on, what we know about in the wintertime, typically there's less humidity, typically unless it just rained, less humidity, temperature is going to fall real quickly. What's happening is as we remove heat and humidity from the building and this refrigerant runs and carries it outside and then rejects it outside, it's going to absorb more heat and it's going to run that outside and dump that. the temperature inside the building is going to lower and lower and lower. There's no heat load. And that's going to cause a problem for just running. And so we're not going to be able to actually measure the refrigerant charge accurately. The other thing is we're not going to have any humidity to deal with as well. So not only your dry bulb temperature, your humidity level is lowering. Yes?
What would happen if we kept the indoor temperature just like it is, but outside warmed up to say 95 degrees, and you had that metering device?
What do you got to look at right now to figure that out? He gave you a wet bulb, an indoor wet bulb temperature, and an outdoor dry bulb temperature. What does it say? What number is it? Is it X? So that X is saying you can't really set the refrigerant charge level at that point in time because it would be at 0 degrees of superheat. It's going to be running with no superheat at that point in time. So we only want to be checking the refrigerant charge when you have a heat load in the inside of the building and it lines up to actual target superheat. So that's what we need to do.
Now, is this a comfortable temperature in here? Yes. Do you have customers that keep temperatures about like this? So what happens if you have customers that have temperatures inside their house about like this? So if you have a customer with a fixed orifice metering device and they keep their house this temperature, but the outdoor temperature rose above 95, does it get that hot here? Sometimes, okay? So what would be happening to that compressor if you properly charged the system on another day and it reached these conditions outside? What would be happening to the compressor? So you're going to see a lot of technicians, depends on where you are, but there's a lot of technicians out there that say they prefer a fixed orifice metering device because it's so simple. It's simply a fixed piston. It's like, oh, there's nothing to break. And that's true. There's really nothing to break. However, just because this is not breaking, is everything okay? So what's the problem? What's happening? If we have that fixed orifice metering device under these conditions, that good old fixed metering device under these conditions, what's happening?
Superheat's decreasing.
Yeah, that's right. Your superheat's decreasing. We get into a special word called saturation, which means liquid and vapor. And how much liquid's coming back to the compressor under these conditions? How much is it liquid? Is it all liquid? Is it 25% liquid? Is it 1% liquid? How much liquid is it getting back to the compressor?
It's difficult to say.
You don't know. But here's what we do know. The compressor only breathes in a superheated vapor. Vapor only. It's a vapor pump. No liquid. It's not a saturation pump. It's not a liquid pump. It is a vapor pump. So what happens when we get liquid to our vapor pump? That's right. You can't compress that liquid. Something's going to start breaking. Now here's the thing. You hear people that say, oh, I've been doing it. I've never had a problem. It doesn't mean that liquid's going to immediately kill the compressor. What it'll do is it'll come in and wash the oil away from the bearings here at the bottom. The compressor will pull that liquid refrigerant up to the top. It'll actually wash the oil away from the moving parts here. And over time, it starts having damage because these moving parts are turning without any oil lubrication. There's just liquid refrigerant. And liquid refrigerant does not lubricate. So what happens to these metal moving parts that are turning very, very fast? Lots of friction. So just because it may be working right now doesn't mean it's going to be working for the long term. It's going to be taking life out of that compressor. How much? I don't know. It depends on how often it's ran, how often there's been flood back. There's a lot of scenarios. So just because it doesn't kill the compressor right away, you hear people that'll say, I've been doing it for 30 years and never seen a problem. Those same people will say, those compressors only last 8 years. Did you know that Copeland Scroll compressors, they build and test their compressors to last 20 years? Still be operating at 20 years. Compressors don't die. They're murdered. One of the big things that murders them is liquid floodback from low superheat. We don't have enough superheated vapor. Compressor starts trying to drink that liquid. It starts trying to handle it. There's people that say, oh, scrolls can handle liquid. They can't. They can handle it better than a reciprocating, but it's still bad for them. It's very bad for them.
If you have a low humidity inside the house, high outdoor temperature, you'll be in the blue. You cannot set that refrigerant charge properly then. And the reality of it is, even if you set it on another day, that's a problem, right? So like people in dry climates, I tell them right away, they tell me where they're located at. Oh, they have a, what's that? A piston, fixed orifice. I tell them, this is going to be more of your solution right there. This and maybe one of these. So if you're in that scenario where Ty's talking about, you need a different metering device because you're just going to kill the vapor compressor. You're starting the system up for the first time. You just installed the system, maybe about 70 degrees, indoor wet bulb. Maybe it's about 90, 95 degrees outside. What is our target superheat? 18. Indoor wet bulb 70. Outdoor dry bulb's 95. We got 18 degrees of target superheat. If we are at 3, we need to recover some of the refrigerant out of the system. If we were at 30 degrees of actual superheat, we need to add refrigerant to the system. So right here as a nifty little thing right here at the bottom, you can read this. It says compare the actual total superheat to the target superheat. If the actual total superheat is higher, this is what actual total superheat is being measured right here. That's higher than the target, add refrigerant. If the actual total superheat is less than the target, recover refrigerant. If the actual total superheat is plus or minus 2 degrees away from what it should be, it's accurately charged. Don't ever set the target, don't ever set the actual superheat any lower than 6. Okay? Which means it may even have to be set inefficiently. So if you are like at 5 or you think it's going to be like at 4 or something like that, you're still going to have to set it at 6. And if you want to learn more about HVAC, make sure to check out our website over at acservicetech.com, where we have a bunch of quizzes, articles, and HVAC books for refrigerant charging and mini splits and other various resources. Hope you enjoyed yourself. We'll see you next time at AC Service Tech channel.